Welcome everybody. So this week I want to do something a bit different. So as I was telling you, some of you before, one way to study for this upper division course is to read the textbook or one of the two textbooks that we have very carefully. And I know some of you know how to do that. Some of you are still learning how to do that. And it's one of the main skills we will get from your undergrad in math, to be able to read something on your own and learn it on your own. And that's kind of the skill that people look on math undergrads. So I feel it's worth going through it. For lower division courses, you just do a lot of exercises. You kind of figure out how to solve things. If you're good at pattern matching, you can recognize a pattern, match it in the exam, and then do it. It doesn't work that well for upper division classes. In these ones, you really have to understand what's going on. And just reading and trying to understand proofs, that's already good enough exercise for you, for your mind to get used to the concepts. Okay, so we're going to continue on the topic of compactness that we've been doing for the last 2 weeks. And I want to look at Miletti's book, which is not our textbook, but it's the secondary textbook that we have. And just read some things from there and show you at least how I go through the process of reading math. When I read math, different people go through different processes, and of course, depending on how hard the material it is for you, you will go slower or faster. But I just want to show kind of like some of the main points, the main things that I would stop at and kind of ask myself, and how it's very different than reading a novel. Let's say, reading math. Okay, so we're gonna see one application of compactness in this video, and we're gonna see a few other ones in the later videos this week. So, compactness theorem. This is compactness for sentential logic. Okay, so here all we have is propositions, which could be true or false, and all we have is the connectives and or implies not, and if and only if. Okay, and compactness theorem is right there, and it says that the main way that we saw already is that if every finite subset of gamma is satisfiable, then gamma is satisfiable. And of course, if you're reading this and you cannot remember what satisfiable is but don't remember exactly, go back scroll back on the textbook or in your notes and make sure you fully understand what satisfiable means. There's no way to kind of keep on reading if you more or less get it, but not exactly. No, you need to understand exactly what satisfiable means. So I meant that there's an assignment that makes everybody true in the say gamma. And then another formulation that we actually showed that was equivalent last week is that if gamma logically implies phi, so a set of formulas gamma logically implies a single formula C, then it's already a finite subset of gamma that is enough to logically imply phi. Okay, so you didn't need the whole set to logically imply it, just finitely much. The proof that we have here, it says here that they're going to use completeness, because in the textbook they proved completeness before, but as I mentioned before, we're going to see completeness in a couple weeks, and then we're going to prove compactness. So okay, we can skip that. And here is an application that we want to see. It's about coloring graphs. So how do you start? You start reading. You should read this on your notes. This is the definition of graphs, which we saw in a previous video. So a graph essentially contains a set of vertices V and a set of edges E. And the vertices are the points in your universe, and the edges, well, the edges are connecting these points. That's what the graph is. And you assume that if A is connected to B, then B is connected to A. That's kind of one of the only properties. So I'm going through this quickly, but I'm going to slow down in a minute once we start reading the actual proof. And this is going to be something about coloring graphs. This is what this is about. This is introducing what this thing is going to be. And this is an interesting problem in given a graph G is an interesting problem in both mathematical modeling and computer science to determine whether we can color the vertices of the graph using a small number of colors, usually, but a fixed number of colors, in such a way that adjacent vertices have different colorings. Okay, so for instance, you all guys know probably this example when you have a map with a bunch of, I don't know, the states of a country or the map of the countries in the world. You want to color each country in a way that adjacent countries don't have the same color, because otherwise you would mix them up. So the question could be, suppose you only have 4 colors that you can use. Can you color all the countries in a way that all countries are assigned, or adjacent countries are assigned different colorings? But then this shows up in many applications all over the place. Okay, so that's the intro. Now let's start reading the way you should be reading this. It's good to have a piece of paper next to you to write notes. It's very important. And just draw little pictures and see if you understand what's going on. Okay, so definition. So please read this carefully before all this introduction. Okay, suppose you have a graph. Vertices V and edges E. And K is a number of n plus. If you don't remember what n plus is, well, it's a positive number, so n without natural numbers but not 0. So all the ones that are actually positive makes sense. Okay, so let's see. So a K coloring is a function, it's defining a K coloring, and it says it's a function from V, the set of points, the set of vertices, to this bracket K. Do you know what bracket K is? If you don't, you have to go in the textbook and go look back and see what that means, right? So it's often the case that either you don't remember, you read it but you don't remember, or in this case we are just skipping into section chapter 3, and maybe you don't know the notation, so you have to look and see what it means. I'm sure it's defined somewhere before, and you would find that K with the bracket is just the set 0, 1 up to K minus 1. So it's a set with K elements, all the numbers from 0 to K minus 1. Okay, so it's a function that assigns every vertex a number 0, 1 to K minus 1. Okay, so if here is your graph, it's assigning a number 0, 1, 0, K minus 1, K minus 1, I don't know, each vertex is assigned a number. Draw a little picture usually, or just at least think in your head what this means, so then you get the intuition of what's going on before you need before you read the next sentence. Okay, so we say that K coloring is proper, so now here defining proper, notice that one is not italicized, if this function f, the function f is a coloring, gives you different values whenever u and w are in E. U or w are in E mean that they are adjacent. There's an edge between them, right? Now we look at the picture and we say, well, okay, here 0 and 0, well, these two vertices are assigned the same value, but they are adjacent, so that's, there's an edge between them, so that means that that coloring is not proper, right? Because it says that they have to be different if there's an edge between them. And then you look at, well, K minus 1 and K minus 1, they are the same, but there is no edge between them, so that's not a problem. There's not a problem there. The only problem is that these two are assigned 0. Okay, so this picture always is things right after you read something. Don't just continue reading before the idea is very clear. Okay, then a graph is K colorable if there exists a proper K coloring of G. Okay, so it's about the existence of a proper K coloring. And now, okay, that makes sense. I don't know how to think about where this makes sense, where this is a trivial definition, where this is hard. And for that, the best thing, even before reading what's coming next, is to have a few examples in your head. Okay, so and usually just start with trivial examples. So I don't know, consider a graph. Let's draw it right here with 3 vertices, and ask, is this 3 colorable? Yes, just 3 colorable. You can put 0, 1, 2. Sure, okay, that's trivial. And then you think, well, if you have k vertices, it's always k coloring because you can put a different color in each one. So that's easy. So then it's only interesting if there are very few colors compared to a set of vertices. So okay, 3 is too easy. What about is this 2 colorable? And then you say, well, for being 2 colors, you can use the color 0 and 1. So if you let this one 0, then the other ones have to be 1s, but then they will have to be the same. So there's no way to assign 0, 1 to all these guys. So this one is not 2 colorable, but then if you put square like this will be 2 colorable. And is there and do we know something that is not 3 colorable? Well, if I added this and this, well, that coloring doesn't work anymore. Can I make it 3 colorable? Well, 0 is touching with this one, so this one has to be 1. This one up here is touching both 0 and 1, so it has to be 2. This one is touching 0, 1, and 2, so it cannot be anything. So this one is not 3 colorable. Play a little bit with things, with the definitions before you move on. Good. Okay, so now we understand what k colorable means. Man, it's an interesting question to figure out when you can do these k colorings. And the proposition that we're going to prove using compactness, this doesn't give you the full answer, but it's in this vein. It says if you have a graph which is possibly infinite, and that in this case means the interesting case when it's infinite. So let G be a graph and K be a number. Then the proposition is the following: if every finite subgraph of K is K colorable, then G is K colorable. Okay? So that's what it says. So when you read the proposition, also before going into the proof, you have to do a couple of things. First, say, okay, so why it says here possibly infinite? Well, because if it's finite, then every finite subgraph is K-colorable already implies, the whole thing is finite, so it's trivial. So that's why, if in the case of finite, it's trivial. Okay, what else we can observe? This is one implication. Is the other implication? Why is it only one implication and not if and only if? Well, if the whole graph is K-colorable, then you can use the same coloring on all the finite subgraphs, right? You can just restrict the coloring to same coloring you use on the vertices. You look at subgraph, it still works. So definitely the R direction is obviously true. So the reason is only stated like if then and not if and only if is because the R direction is trivial. This is the only interesting direction. Okay, so that's why. What else you should think about? Well, you should think about if whether you picture this theorem. Well, is it like difficult, hard, crazy? Maybe the first thing you say was like, well, look, if you have a finite subgraph and it's K colorable, then you have a K coloring of a bigger one, a K coloring of a bigger one. Just put them all together and it works. Isn't that too easy? And then you're like, wait, no, because if this one is K colorable and then you take a bigger one, all we know is that it's a K coloring, but maybe it doesn't match the original one. So you couldn't put them together because maybe the coloring, or maybe you have two different ones and you can K color this one and K color this one. And then you say, well, we just put them together, but no, because there are edges in between them. So if you color this one without thinking of this one and you color this one without thinking of this one, then the edges in between are going to be a problem. So you couldn't do that either, right? So think about like easy proofs that are come and maybe one of those works, and if they are, or see why they don't. Okay, so then you see, well, okay, it's not trivial. This is not trivial at all, because just knowing how to color every finite subcoloring doesn't tell you how to put together all these subcolorings because they might not be compatible. So okay, so then the other thing you should do is usually try to think about the proof yourself a little bit before you read it, at least to know what that you have to do. And we know we are in the setting of compactness, so there has to be some compactness involved. I mean, this is compactness for sentential logic, so we're not going to treat the graph as a first-order logic. We're going to have to somewhat develop sentences which have true values, true or false, and use truth assignment for these sentential kind of variables to mean something that we want, probably the coloring, right? Okay, so you can think about it before, maybe nothing comes up, and then you start reading. Okay, so let's see what it says. So here it starts with the idea before it goes into the proof. And sometimes you read the idea and you have no idea what it means. Sometimes you do, and then you can figure out the proof yourself. Sometimes you read the idea, you don't know what it means, then you read the proof, and you understand, and then you give back the idea, and you're like, okay, that's the idea. So play with those things. So the idea is to introduce propositional symbols A, U, I. Let me draw that bigger. A, U, I, where what's U and what's I, for each order pair consisting of a vertex U. So the U represents a vertex in the graph, and the I represents a number from 0 to k minus 1, which these are what we're using to as colors, right? So our colors are the numbers from 0 to k minus 1. So that's what those are. So for each color and each vertex, we have a sentential symbol AUI. And as you will expect, intuitively, the truth assignment, a truth assignment M, which assigns this variable 1, okay, and then 1, in the course we were using true and false. So look back in the textbook to see if why is they're using 1 and not true or false. And it's because for this textbook, 1 is true and 0 is false. Okay, you look it up, you come back. So if we assign 1 to this variable AUI, that means that we are coloring vertex U with color I. Okay, so AUI means vertex U is color I. And then you can write that on your piece of paper just to remember what that is, or you can highlight here. This means color vertex U with the color I. Okay. We now want to write down the formulas that essentially say that the coloring that we're going to get is what we want. So it satisfies that if the truth assignment, a truth assignment will kind of give you a coloring, but it has to be correct. It has to be a proper coloring, and it has to be an actual coloring. So each vertex must be assigned a single coloring, not many colorings. So let's see how we write all that together. And then you say, okay, maybe I can figure it out. Maybe now with this idea, let me try to do it before I read. Okay, do that. And now come to read and see if it matches what you did and if you maybe forgot something or not. Okay, so we continue reading. Okay, so let P be the set of all of these sentential variables, propositional symbols, that's what they call them here, for U in V and I a color. Okay, so remember, and then what is P here? Well, if you look back, P here is what they are using for the set of propositional symbols or sentential variables. So these are all the sentential symbols we're going to use in this course. And now let gamma, which is going to be our set of formulas, be a union of all the following sets. Okay, first, this one up here. Okay, this is a weird notation, which you haven't seen in class. Again, you have to look back in the textbook and see what that means. But maybe you can guess. It's kind of like for summation, you use like the sigma sign when you add many things. Here is kind of like a summation. So this means AU0 or AU1 or AU2 or dot 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 AUK minus 1. The disjunction of all of those is written with a big or sign of all of them. Okay, and this is saying, and what is it saying? Then think about what this is saying. This is saying that vertex U is either color 0 or 1 or 2 or k minus 1, so one of them. So this is saying that vertex U must have a color. Okay, so think about it, what it says. That's what it says. And then whenever we have, for every vertex U, and every time you have two different colors, a vertex can have two different colors. It must have only one color. So this sentence up here is going to say that you can only have one color. Okay, so look at it and see what it means. Okay, so far we have that every vertex is assigned a unique color. Okay, so we continue in the next page. What else do we have? And so far we have that every color, every vertex is assigned a color, so we have a coloring. Now we have to say that it's proper. And to say that it's proper, we had to say that whenever we have an edge, so two vertices in an edge, and we have a color, they cannot both have that color, right? So for every vertex and every color, every two vertices that are sharing an edge, they two cannot have the same color I. So you write the sentence that says it's not the case that U has color I and W has color I also. Okay, and then you think, is this enough to ensure that we're getting a proper coloring? And you think about it, maybe draw a little picture and say, yeah, that should be enough. Okay, so now we're gonna use, so now we have this, so now we know that we have the right sentence, and now we want to show that it's satisfiable using compactness. Okay, so what do we do? Well, let gamma 0 be an arbitrary finite subset of gamma. Okay, it makes sense, because we have to show every finite subset is satisfiable. Good, so far that's what you expect. So this finite subset is using some elements of V. So let U1 up to Un be the set of all the elements U in V such that AUI occurs in some element of gamma 0 for some I. And then you have to think about what that means a little bit. Right, so in gamma you have these formulas mention some of these variables, AUI, for different I's. So it's maybe the same U with different I's. And read it again, it says, well, take all the U's such that some variable AUI is mentioned in this gamma 0. Okay, so far so good, and maybe you can even draw a little picture so you have your graph, which is very complicated because it's infinite. But then you say, well, now we're only considering finitely many of these guys. Okay, so we picked all the ones that are in the gamma 0, and then remember we need to show that gamma 0 is satisfiable. And then now we use the hypothesis, since every finite subgraph of G is K colorable, we might fix a proper K coloring of F. Of F of U1 up to Un. These are the ones that we are using in gamma 0. Of the graph, of the subgraph induced by these guys. So essentially we only consider the edges between these guys, and we consider that subgraph. And now we want to show gamma 0 is satisfiable, so that means we need to give a truth assignment. So what is the truth assignment? We assign each of, essentially we only care about the variables that use these U's that show up U1 up to Un. So we say that if you're given AWI, if W is one of these UIs and F assigns that guy to I, then give true. And if W is not one of those, or it is one of those but the coloring is a different one, you give false. And again, remember, you have to look it up. This means true, this means false. Cool. Okay, so what have we done? So we have a truth assignment that on these guys uses the proper coloring, on the other ones doesn't. And then if you look at all the sentences in gamma 0, well, we don't know what they are, but we know that the sentences in gamma 0 are a subset of gamma, so they are among these ones and the ones we had in the previous page down there. So and we know they only use vertices v0 up to v1. So among all the formulas that may show up in gamma 0, they only use those vertices. If you look at each of them, this proper coloring makes them true, right? For each vertex, only one is at least one is colored, but only one, and adjacent vertices have different colorings. So that's true. So that means gamma 0 is satisfiable. So if this is not obvious, slow down, stop, and look at each of the formulas on these three sets of formulas and make sure they are all satisfied in this case. Okay, and then why was this so easy? Because we are only using the fact that this is finite, and we are not worrying about the truth assignment outside these guys, because this works. We only need to show the gamma 0 is satisfiable, not the whole thing. Okay, so fill in the gaps. So gamma 0 is satisfiable, and then by the compactness theorem, it follows that gamma is satisfiable. So if you don't remember, you have to read what the compactness theorem says, which version are we using. If every finite of gamma is satisfiable, then gamma is satisfiable. Okay, so what does that mean? What does it mean? So now we have a truth assignment from all the variable to, again, 0, 1, and if it confuses you, write it down, which makes all these formulas in gamma true. Okay, so what is it saying? Well, now notice that for each v, there is a unique I that it makes it true. This is because the first set and the first two sets of formulas, and if we define, so that means if there is a unique, for each u there is a unique I that makes it true, then we can define this function f of u to be that unique I that makes it true. And then the third set of sentences, this one up here, is telling us that whenever we have an edge, those two vertices in the edge must have different colors. So we have built a proper coloring, and therefore we get that G is K colorable. And what's that what we wanted? Yes, that's what we want. And then you finish the proof. Sometimes you finish the proof on the and you could follow the step by step, but you still don't see whole picture. So you usually slow down and then see if you see the summary of the proof in your head, which is okay. So we had we build a set of sentences so that if we're having the intention that if we have a truth assignment, we're gonna get a K coloring for G, and then to show that such a truth assignment exists, we're going to use compactness, and then we're going to use the fact that every finite subgraph is K colorable, which we use along the way, and that's how the proof goes. Make sense? Cool. Okay, so we'll continue with a couple more proofs in the next